14th lecture on natural response of second order circuits continued. We have been discussing two cases, that is capital D greater than 0. In this case there are no oscillations. The solution consists of the sum of two exponentials, e to the minus s1t and e to the minus s2t, where s1 and s2 are both real and negative. Alright, e to the s1t minus e to the s2t, a1 plus a2. This is the solution, where s1 and s2 are both negative, there are no oscillations, so the current starts from 0, attains a maximum and then goes to 0. On the other hand, if D is less than 0, then we have oscillations. We have V0 by L omega 0 e to the minus alpha t sine of omega 0 t. Alright. The borderline between these two, or the transition case, which happens at D equal to 0, occurs obviously when R squared by 4L squared is equal to 1 over LC. Alright, this is a very special condition, and the condition on the resistance R to satisfy this is called R critical. It's a critical value of resistance for which this shall be true. Alright, if this equality becomes an inequality, there shall be either oscillations or no oscillations, and therefore this is a critical case, and this case is called the case of critical damping. Critical damping, that is, if the damping is slightly less, then there shall be what? There shall be oscillations. If the damping is slightly less, there shall be oscillations. Alpha is the damping coefficient. If the damping is slightly more, there shall be no oscillations, and therefore this case D greater than 0 is called an overdamped case. Overdamped means no oscillations in the natural response, and naturally D less than 0 should be called an underdamped case. Alright, underdamped case, and D equal to 0 is the so called critical damping case. Critical damping, it determines the boundary between oscillations and no oscillations. Let us see what the solution to this case is. Our S12 was equal to minus R by 2L, and since capital D equal to 0, there is nothing else, plus minus 0, and therefore the two roots are now coincident on, if you take the sigma j omega S plane, coincident where? On the negative real axis. There are two roots. At this distance is equal to R by 2L. The two roots are no longer complex, they are both negative real and they are coincident. Now what is the solution under this condition? Obviously, if we take our general solution, if you recall, e to the s1t plus a2 e to the s2t, and if s1 is equal to st, obviously the two solutions are no longer independent of each other. Isn't that right? They are identical solutions in fact, except for the constants a1 and a2. Well, if s1 and s2 are equal, I can always write this as a1 plus a2 e to the, let's say, s1t. If S1 is equal to S2, and therefore this cannot represent the general solution. The general solution must have two arbitrary constants, because it is a second order system, it must have two arbitrary constants, and the two solutions should be independent of each other. They should be independent solutions. And as you know in the solution of differential equations, the solution in this case shall be given by A1 plus A2 times t e to the power, let's say S1 or S2, S1t. Alright. This is the general form of the solution. If under the this is the case for critical damping, that is capital D equal to 0, or which means that R squared equal to, well, r would be equal to r squared by 4l squared, r would be equal to twice square root of L by C. Is that correct? Alright. So this value of resistance is called the critical value of resistance, is R critical, and under this condition this will be the general solution. Now if I apply the initial conditions, that is I0 equal to 0, then obviously you see A1 should be equal to 0. Is that right? If I put t equal to 0 here, then obviously A1 is equal to 0, and therefore my I of t shall be equal to A2t e to the power S1t. The second boundary condition, second initial condition is that L di dt at t equal to 0 should be equal to V0, should be equal to V0. If I differentiate this, then I get L A2 t S1 e to the S1t plus e to the S1t, that should be equal to V0 at t equal to 0. I have differentiated this expression, and I have to put t equal to 0. If I do that, then what do I get as A2? A2 is V0 by L. No longer omega 0 comes, alright? A2 is V0 by L, which means that my total solution is given by V0 by L t e to the S1t, where S1 is equal to minus R by 2L. This is the solution to the equation when the two roots are coincident. For example, if L is equal to 1 Henry and C equal to 1/4 farad, what should be the R critical? Twice square root of L by C, 4 ohms. In other words, if R is greater than 4, then this case will be which one? Over, under, over damped. If R is equal to 4 ohms, of course, this corresponds to critically damped case, and if R is less than 4, then this is the under damped case. Alright. Now let's look at this situation. Let's look at this situation in the S plane, alright, the complex plane. And I will repeat what I have been saying in terms of the complex plane. You see, if I have three situations. One is capital D greater than 0, capital D less than 0, and capital D equal to 0. Alright, and the roots of the characteristic equation, let me show the axis, sigma j omega, sigma j omega. There are three cases, and you see in the first case D less than 0, there are two negative real roots, minus S1 and minus S2. In the second case, that is the underdamped case, we have two complex conjugate roots, where this distance, this point is minus alpha and this point is j omega 0, this point is minus j omega 0, alright, minus alpha plus minus j omega 0. On the other hand, if I have the critically damped case, then the two roots coincide on the negative real axis. Alright, is it okay? Let's consider a fourth case in which capital R equal to 0. Can you tell me where the roots should be? On the imaginary axis, okay. Can you tell me the value? 1 by LC. In terms of omega n, it is j omega n. Is that okay? Right? Now I want you to look at this figure carefully. If the figure is too small on the monitor, I can draw it again, enlarged version. Can you Can you see distinctly from the last bench? Okay. Now look at this case, d less than 0. This is omega 0 and this distance is alpha. So what is the distance of the root from the origin? Omega naught squared plus alpha squared. Isn't this simply equal to omega n squared? Okay. Now omega n depends on L and C only, isn't it right? Omega n does not depend on R. Is that clear? By definition, omega n is the undamped natural frequency of oscillation and undamped means R equal to 0. It is this omega n we are talking of. On the other hand, both alpha and omega 0 naturally depend on R. Is that clear? Because alpha depends on R, alpha is equal to R by 2L, therefore omega 0 depends on R. Omega 0 squared after all is omega n squared minus alpha squared. Is that clear? I am trying to introduce a concept, so please be with me. What I have said is omega n is independent of R, alpha as well as omega 0 depend on R, and therefore if I take a circuit, if I take a second order circuit, C, L and R, and if I adjust R, how do the roots change? How do the roots change? Alright, this is what I want to find out. Suppose I wish to draw the roots of the characteristic equation on the S plane. Then when R is equal to 0, start from the 0 value, it cannot go below 0, alright. When R is equal to 0, where are the roots? Roots are on the imaginary axis at plus minus j omega n. Is that okay? When R is slightly increased, what happens to the roots? They move to the left half plane. This is the right half plane, this is the left half plane. They move to the left half plane such that the distance of the root, distance of either root from the origin remains a constant, and that constant is equal to omega n, and therefore the movement of the roots shall naturally be on a semicircle where this distance is omega n, alright. Is that clear? As R is increased, this point corresponds to R equal to 0, and as R is increased, the roots, the two roots, this root moves in this direction and this root moves in this direction, such that they are always complex conjugates, but they must remain on the circle, alright. Now when the roots approach each other and meet on the negative real axis, what is the situation? The two roots have coincided, and therefore capital R must have reached its critical value. So this point shall correspond to R equal to twice square root of L by C, where the roots become coincident. Roots are no longer complex, they are real, negative and coincident. Alright, what happens after this? They move on the real axis. Well, what happens is, you recall that the roots are minus R by 2L plus minus square root of R by 2L whole squared minus 1 over LC. Now when capital D, this point corresponds to capital D equal to 0, alright, that means the roots are at minus R by 2L. Now when resistance increases further, what happens is that this minus R by 2L is either added to a quantity less than it or subtracted, that is a negative quantity which is less than it is added to it. What does it mean? It means that the roots, one of the roots goes towards the origin and the other root goes towards infinity. Alright. If capital R is increased beyond the critical value, the two roots, the case is that of over damped case, and the two roots move along the negative real axis. The roots always remain negative real. One increases in magnitude, the other decreases in magnitude. The one that decreases naturally goes towards the origin, and the one that increases goes towards infinity. Alright. This can also be seen from the analytical expression. Try to follow this very carefully. When capital R tends to infinity, when capital R tends to infinity, one of the roots should be 1 by LC naturally can be neglected then, and therefore one of the roots should be minus R by 12 minus R by 12, and the other root would be minus R by 12 plus R by 12. So one of the roots goes to the origin, the other goes to infinity. Is that clear? Okay. So both from the analytical expression, from explanation, and from the figure, you can see that the locus of the two roots is given by this semicircle, and then two straight lines, one going towards the origin, the other going towards infinity. And this picture which gives the motion of the roots or the locus of the roots as one of the parameters, capital R, changes in the circuit, this picture is called a root locus. For obvious reason, it describes the locus of the roots as one of the parameters, that is capital R, changes. Now if you argue what is so sacred about capital R, why don't you keep R constant and vary L? We can again obtain another sketch which will not be exactly this. It will be another sketch, but you can draw it, and I leave that to you as an exercise. Once again, you can obtain a critical damping condition, an under damped condition, and an over damped condition. You can also draw a root locus for variation of capital C. Capital C can also vary, and this would be a third kind of sketch. Now is this point clear? The concept of root locus, the concept of over damping, under damping, and critical damping. Alright. Usually in measuring instruments which can be usually modeled as a second order system, what do you think we should have as far as damping is concerned? Critically damped. Well, why not under damped? Let's understand.
If we have an under damped system, then it keeps oscillating about the actual position, and we don't get the exact value in a small time.
That's right. It takes quite a bit of time. The needle goes on oscillating, and then finally it settles to some value. Whereas if it is critically damped, then it reaches the final value. All right. If it is over damped, then it takes a very long time to reach a steady state, and therefore these concepts are important. The concept of root locus, as we shall see, is extremely important, arises in control systems, arises in many other physical systems. The other concept that is of extreme importance is that of impedance, and this is time that we introduce this concept, impedance. I shall first give a formal definition. Yeah.
Before we move on to impedance, could you tell us what exactly is the purpose of finding the root locus?
Oh,
Second order system.
It shows the locus of the roots as one of the parameters is varying.
So that's okay, that's obvious, but I mean, what is its importance?
No, what is its importance? Well, as you shall see later, if you are a mechanical engineer, in control systems, in any process control, for example, which can be modeled as a second order or third order or fourth order system. Suppose the roots, one of the roots, due to a disturbance in a parameter, goes to the right half plane. If the root locus includes the right half plane, what will happen? Or the imaginary axis, then what will happen? Suppose the parameter is such that the roots are on the imaginary axis. Then the instrument or the process that you are experimenting with will never settle down. It will go on oscillating. Isn't that right? So the root locus shows the locus of the roots on your design should be such that the roots are in the left half plane. For example, it is not always true that in all physical systems we require a critically damped case. No, sometimes a bit of oscillation is necessary. Why? If you want a quick response, well, after a couple of oscillations it stays, it settles. So a little bit of damping, a little bit of under damping is quite in order. So the root locus shows where to locate your roots, and if you know where to locate your root, then the system design is obvious. Alright, so this is the purpose of the root locus. Root locus is an analytical tool for designing a system. I have drawn the root locus of a second order system. There can be third order, fourth order. Usually natural systems, practical systems are usually second or higher order systems, and the root locus is essential for determining the design criteria. Where should you locate the roots in order to satisfy what you want, in order to satisfy your requirements? Is that okay? Any other question regarding root locus? All right. Next, we introduce the concept of impedance. The introduction or the definition that I am going to give you now would be a bit heuristic, a bit inaccurate, a bit unsophisticated, but this will serve our purpose at the present moment. The definition of impedance is like this. Consider a two-terminal network, a network which is only two terminals, all right, and you consider a linear network, all right, a linear network. Then you know that all that you can do is to connect a voltage generator and measure the current. The excitation would be a voltage generator, the response would be a current, or you could connect a current generator here and measure the voltage. All right. Now, if your excitation, either a current generator or a voltage generator, is of the form of e to the st, and this network is a linear network, contains resistance, capacitance and inductance, then you know the differential coefficient of e to the st is also of the form of e to the st, s times e to the st. The integral of e to the st is also of the form e to the st. So if you apply a voltage generator here which is of the form e to the st, the current shall also be of the form e to the st. Isn't that right? Similarly, if you apply a current generator which is of the form of e to the st, the voltage developed across this shall also be of the form e to the st, and therefore the ratio of V by I, the ratio of V by I shall be a constant, but it will depend on the value of S, and therefore this is denoted by capital Z of S, and this is called the impedance. I must caution you. So let me first define it. The impedance of any two-terminal, any linear two-terminal network is the ratio of voltage to current provided the excitation, either the voltage or the current, excitation under bracket, either the voltage or the current is of the form of e to the power st. Is that clear? It is not true for any arbitrary excitation. Excitation must be exponential. Only then the ratio of V to I is called an impedance. Let's take an example. Is the definition clear? The exponential excitation is an integral part of this definition. If that part is taken out, then it doesn't make sense. All right. For example, if I take a resistance, let's say a two-terminal network, a pure resistance R, then you know V is equal to IR. and if V is of the form of e to the st, I is e to the st divided by r. If I is of the form of e to the st, then V is e to the st multiplied by r, and V by I is equal to r. This is a constant independent of S. Alright, this is a constant independent of S. On the other hand, if I have an inductor L, V and I, then you know V is equal to L di dt, and therefore if I is of the form of e to the st, then V by I shall be equal to S times L. So the impedance of an inductor of value L is simply equal to S times L. Alright, what is the dimension of S? 1 by time, which means S is a frequency, and S could be real or complex. Alright, so in general small s is a complex frequency. Real frequency, real quantity is a special case of a complex quantity. Isn't that right? So if you view life as complicated, this is the most general situation. If you take the imaginary part out, life becomes simple. Alright? So S is a complex frequency, and the impedance of an inductor ZL of S is equal to S times L. If I take a capacitor C, you know the current I equal to C dV dt, and if V is of the form of e to the st, then Z of S is given by 1 over S times C. This is the impedance of a capacitor ZCS. Alright, and once the impedance is defined for inductor and capacitor, you can treat inductors and capacitors exactly like resistances. Alright, the impedance of a resistance is R, the impedance of an inductor is S times L, the impedance of a capacitor is 1 by SC, and if you have, let's say, a series combination of R, L and C, then your V shall be equal to drop across R plus drop across L plus drop across C, and if you take the voltage or the current of the form e to the st, you can show that Z of S here of R, L and C in series is simply given by R plus SL plus 1 over SC. That is, these quantities can now be added. Alright. Similarly, suppose I have a circuit like this, R, L and C. Suppose I have another combination. This is not a series combination, it is a series connection of R with a parallel connection of L and C. If this is V and this is I, and one of them is exponential, then the impedance of the circuit can be written, the manipulation will be exactly like that of resistances. Here an impedance SL is in parallel with an impedance of 1 by SC, and therefore it is R plus SL times 1 by SC R1 R2 divided by R1 plus R2. Now instead of R you say Z, the impedance. So Z1 Z2 divided by Z1 plus Z2, that is SL plus 1 over SC, which is equal to R plus SL divided by S squared LC plus 1. Now you ask me, what is the use? Why should we do that? Well, if we do this, if we define an impedance, one of the advantages is that all kinds of circuits can now be treated in exactly the same manner that you have treated a resistive circuit. For example, Thevenin's theorem. With this definition of impedance, now Thevenin's theorem is applicable to RLC circuits also, Thevenin's Norton's. And we can also do circuit analysis without writing a differential equation. Once the impedance concept is introduced, d dt shall be replaced by S, an integral shall be replaced by 1 over s. E to the st dt integral is e to the st over s. d dt of e to the st is s times e to the st. Alright, let us take a specific example before we close this class. Yes, please do.
Sir, for considering impedance, has the applied voltage or the current, whatever it is, has to be the form of e to the st.
Exponentially.
But sir, if we consider charging of a capacitor, sir, we don't apply a voltage of form e to the st. But still, the voltage across our capacitor can be given as e to the st. So can we say, like, can we define an impedance for it?
That is a generation of e to the st, generation of an exponential wave form. That's a question is completely different. This question is that of combining networks. You see, if you simply want to charge a capacitor, now here e to the st does not come into effect because your voltage, your source is a constant. It's not of the form e to the, it is e to the st with s equal to 0, and therefore you cannot introduce impedance concepts here. Alright, impedance concept will come only when the source is an exponential. Let's take one example. Let's take the same circuit that we have been talking of. Let's say R, L and C. Now please pay your attention to this. We are doing something new. Alright, suppose R equal to 2 ohms, L equals to 1 Henry and C equals to 1/4 farad. Alright, and this V is given as 6 e to the minus 2t. Isn't it of the form of exponential? It is an exponential with s equal to minus 2. So if I wish to find this current, let's say I, for example, then what I do is I first find out z of s. Z of s, as you have seen already, is r plus sl divided by s squared lc plus 1. Now substitute the values. Z of minus 2, alright, would be equal to 2 plus s is minus 2 multiplied by 1 divided by s squared is minus 2 squared times 1 times 1/4 plus 1, which means z of minus 2 equal to how much? 1. Alright, z of minus 2 is equal to 1. So what do you think this current shall be then? V by I is z of s, so it will also be 6 e to the power minus 2t. Is that clear? Is it minus? No, it is plus. I shall be equal to V divided by z of minus 2, and therefore it is 6 e to the minus 2t. What do you think this voltage shall be? V1. It would be V minus IR. So what would this be? V is, so this would be minus 6 e to the minus 2t. I know this voltage. If I know this voltage, do I know this current IL? IL shall be equal to this voltage divided by SL, where S shall be equal to minus 2. Do I know this current IC? Yes, it would be C dV dt. C dV dt, that is the differentiation of this. So I know all currents and voltages in this circuit. You see, the excitation was exponential. I did not have to write a second order differential equation. Normally, yeah. You wanted to ask a question? Normally, in a circuit like this, I have to write a differential equation and then solve it. That is, write a1 e to the s1 t plus 8. I didn't have to do anything like that because I recognize that the excitation is exponential. And if the excitation is exponential, I can work purely in terms of impedances. Alright? I will just, 5 minutes, I'll just introduce another term to you. It is admittance. I told you impedance is the ratio of voltage to current the reciprocal of an impedance is the admittance. Admittance is 1 over impedance. Sometimes it is easier to work in terms of admittance rather than impedance. And it is with this that we conclude the class today.